right, for everybody that's here, I'll project loud. Um, One thing we're doing today is we're also going to be on Zoom. So there's an audience out there. Welcome to today's demonstration. I'm Professor Barron, Andreas Weisman. I've been at Utah State for almost 6 years. When I got hired on, they asked me what I knew about UAS. And to give you a 30-second background, I said, well, in the Air Force, I worked with drones and some different aspects, but we can work on education program. And so we're honored to have Mac McGee here. We actually sat down with Cal and Alfonso Ian and Dan Robinson, Wookie, who's recovering in the hospital right now, not here today with us. But it was interesting how we sat down and we wanted to come up with this idea of trying to get some drone education. And over the last couple of years, we've developed a drone minor, and we have almost 100 students in the drone minor. We've added classes and expanding our program, and we're now in the process of proposing a drone certificate for US Eastern campuses, and eventually a drone major and a master's program here. So we have come a long way with that education side. Now we're ready to start branching more into the research side, but AggieAir has been here for almost 2 decades in some form or another doing some research. And so we have a great partnership, whereas I'm training students, undergraduate and graduate students, and then Cal Koopmans hires them to work with AggieAir. So we're ready for that next area. We started a class this fall about drones in agriculture, introduction class. And our goal is next summer to have a precision agriculture class flying what you see out here. So we are in the process of trying to look for some grant opportunities, internships for our students. And so folks out there, and that's why we decided to make it a department meeting with the College of Ag, is we've got some talent with our students and interest. You may have some opportunities with research funds, and we've got an incredible experience with AggieAir. So Cal Koopmans, I'll introduce him. He is the one who will show and showcase what AggieAir is doing. If you have more questions about the ag, or about research in drones or drones in agriculture class, come talk to me afterwards. But today's focus is on doing a demonstration of their latest technology that they just acquired, how they're going to use it, how they use it already, and how you can use and partner with AggieAir to help out in your programs. And so I'll turn the time over to Cal. Take it away.
Thank you for that great introduction, Baron. For the rest of us playing at home here, I think we have 16 participants. If you guys have a question, you can raise your hand on Zoom, and hopefully we can get to you. While we're getting started here, let me go over a little bit of a schedule of the events. I am going to be here giving everybody an introduction to the AggieAir program and the technical capabilities, basically what we do and what it looks like. And then we will have the live flight demo, which is happening outside, which will be also broadcast on Zoom. So during that, we can see the aircraft take off and fly around. And while it's in the air, we're going to be taking you through the scientific calibration process, the truck and the trailer and everything outside. And for that, we'll be guided by Alfonso Torres, who is a professor in the civil engineering department here at USU. And then we'll come back inside and we'll finish the slideshow and show you some examples of the kind of information that we've collected with AggieAir. Basically, the point is data, right? So we'll show you some of that information. And then we'll have a Q&A session, and the aircraft will land, and basically it'll be a networking event after that. So to get started here, I believe showing my screen, and the audience here, you can see my screen and me, so you get to me. This is just kind of a potpourri of what AggieAir can offer, and what we've been up to and why. But because I'm a professor, I need some charts. Can't have a good presentation without a chart. Let me see if I can move this out of the way. There we go. So what is AggieAir? Well, our motivation is scientific information collection via drone. So drones for science. How do we do that? It's a systems engineering process. This means we start with the teal square on the bottom. This is an area of interest, and inside that area of interest, we have scientific questions. Well, what kind of questions are scientific? That's an interesting kind of quandary. What it means is when you ask the same question in the same way, in a scientific way, you get the same kind of answer. That means you can rely on it, and you know the next time you ask it, you can rely on that one too. And that means you can make decisions based on scientific information. So a scientific question requires science to provide the answer. So we have an area of interest in this case, the teal square, or the experiment farm here where we're at. We ask these questions, and if we do it in the right way, that sets the engineering requirements for the data. So that means, well, what data do we need to answer this question? Well, that's set by the area of interest and basically the scientific motivation. So we have these data requirements. Those data requirements mean what we need to answer the question. How do we do it? Well, those set sensor requirements, and the sensor is the actual object which senses the data. Now that we're in sensor requirements, that means we can start doing the engineering. So we transferred the scientific question into an engineering task, and that means we can set requirements for the payload, which is a collection of sensors. Those sensors, when arranged so they meet all those other requirements, then set something we call the payload. The payload is a collection of sensors. This is more or less a brick where everything happens all at once. The reason we do that is so we can stick it inside an aircraft. So the payload sets our aircraft requirements, thereby meeting everything else. Once the aircraft requirements are set, then we understand how the aircraft flies. We understand other legal requirements, safety, this kind of thing. That sets our mission requirements. So what we're doing today is giving an example of the missions that we've been doing all summer with our new aircraft, GreatBlue. So this is like going to E&J Gallo and imaging their vineyards. Those are the missions which have been defined by all of these other ovals. So when the mission is executed correctly to our standards, the training, et cetera, that produces the purple arrow, actionable information. That means something that you can decide to take action on, and naturally it'll act on the area of interest. And so this is kind of like a closed loop idea. But if we start with the end in mind, we might actually be able to get there. And that's what AggieAir has been doing. This is like a general systems idea, but specifically for us, this is aerial data that answer these scientific questions. Okay. So what about AggieAir? AggieAir is a research lab at Utah State University under the Utah State University Water Research Lab. And we have been since 2006, so this is year 14. We're a multidisciplinary aerospace research group focused on scientific remote sensing, which we've thoroughly defined. But we've been here since 2006 doing this, collecting aerial information from drones. You guys in the audience here probably know where Logan, Utah is. For those of you who don't, there's a small map here. We're about 30 miles from the Idaho border, and that means we're in between Pocatello and Salt Lake City. It's a really nice place. You should come visit someday when there's not a pandemic. We have about 30 members, and we count many different members across many different communities as members of AggieAir. Both internally, we have students, grad students, undergraduates. We have other professors we work with, and externally, we have lots of partners across the US and actually the world. This means actually from first year to postdoc. We take people who are just starting their first year of engineering school who say, what is drones? I want to know about it. And they'll come in here and we can teach them and they can contribute. And even if it's just learning how to communicate about drones is very important. And then the end of the beginning of the start of the academic career, postdoc, we have those too. So, if you have a PhD and a hankering to do drone research, we could support that in an academic fashion. So here are some pictures from previous missions. We have flown various places. This is Northrop Grumman's Unmanned Aerial Testing Center. This is Promontory, Utah. And then on the bottom left there, that's actually a vineyard from E&J Gallo. And I think it's Borelli, California. So what is special about AggieAir besides all of the systems engineering? Well, we actually fly in the real airspace with manned aviators, and we have a very good safety record doing this. This is a civil aerial operation. So we have good airspace access, and I'll help you understand what that means. At the state entity level, Utah State University can apply for and receive something called a COA, or Certificate of Authorization. And this is a way of granting a particular aircraft or crew access to airspace. This means with a COA, we can access airspace that's above 400 feet above the ground with our unmanned system, even all the way up to 5,000 feet above ground level, which is an unprecedentedly high amount of access because the manned airspace starts at 500 feet. So this means we are granted, actually we have a active COA north of Ogden, Utah to the Idaho border. So this is hundreds of square miles. This is the 3,000 feet above ground. We've been getting COA approvals and flying legally for a long time. And we really are proud of our relationship, both with the FAA and the airspace itself. And Cache Valley, Utah, we are within a 3/4 of a mile of the Logan Regional Airport. Actually, physically where we're at right now is where we can fly. So we've been doing this for a long time. We have 1,300 plus operational legal U.S. flight hours above 400 feet above the ground. And as far as I know, we're the only group who can claim this. We have a service fleet of 10 aircraft and growing. Actually, I should update this more now, but we have a working relationship and we're proud of representing the values of the FAA. And if you want to know more about some of this, we have flown urban beyond visual line of sight legally. We did this last year in downtown Reno. This was in the NASA TCL4 demonstration. So I'm happy to follow up on some of that stuff, but let it be known, data is the mission. Maybe it's burning behind me, which is always true. But all of this is to say, the point is to fly and conduct this research about how unmanned systems laden with a payload perform in the air and how the data can be used once it's collected safely. So a few antiquated slides or systems. You probably all, when you think the word drone, you probably think of something like on the top left there, VTOL multi-copter. That's a big one, you know, but it takes off and lands without a runway. It can carry some weight and it's got big blades that chop up the air. They're widely available. They're easy to pilot. Generally, they fly less than 400 feet, and the reason is they don't have enough energy to get up much higher. So it's not really worth flying them much higher. But if you fly it, you get about a half-hour flight time, depending on the payload. They're really good at a lot of things, especially if you're trying to film Vin Diesel, you know, careening around a curve on California highways. Yeah, sorry, Slack is busy today. The thing about the VTOLs is they can't carry a lot of payload weight around a large area. If you're trying to do a survey, which is what agricultural applications are really defined as, is a large amount of land. And so a long time ago, AggieAir, this was in 2009, something like this, we decided that we would have both multi-copter and a fixed wing option to do both kinds of missions. And so the fixed wing pictured here is the Aggier Minion. This is something that was in rotation, in production, if you will, for 8 years almost. This is a aircraft that weighs about 20 pounds with the payload. It is launched by a pneumatic launcher, and it pulls like 14 Gs, so it's like a little mini rocket launch. And then it gets up and it flies autonomously for almost an hour. And then it can fly higher than 400 feet, but it requires an expert pilot because when it comes down for a landing, that's like a little crash landing. And so besides the complications of flying a fixed wing aircraft, which take more talented thumbs, the entire system is basically hit like a golf ball into its mission and then lands and skids to a stop. And it might do that gently or probably not. It's a little crash. And what we were trying to do for the last couple of years is make a bigger version of this because we wanted to fly 2 to 3 hours. And that means we could get pretty high. We could fly beyond line of sight, hypothetically, for a grant in the authorization. We could carry heavier payloads and basically be a scaled up version of the good fixed wing. Well, we're here today to appreciate this system. And if you take a look at it, it's actually kind of like all of those system designs all crammed together. We have a 10-foot wing, a tail, and a vertical takeoff and lift system, which is a quad rotor. So what is that? Well, here is the most dense fact sheet we have about it. This is an all-electric aircraft, and it carries our scientific payload up to 11 pounds if you really want to. This is a 2.5-hour flight time. So that means you charge it up, and you could fly 2 hours easily, 2.5 hours with the right wind. All electric, rapid deployable. It's a 2-person crew. And we have an example of this out here if you want to look at the crew and everything. But the key difference is it takes off vertically and then transitions. So it's got a big wooden propeller in the back, and that's where it gets all its efficiency. And it can launch and land without needing a runway because it can descend vertically too. So it's nice and soft. Cruise speed is about 50 miles an hour. And that's actually kind of nice because for a big aircraft like this, they usually go faster. But in applications like ours, we want to go slower so we can take more scientific pictures, basically, slower frame rate. We can take off and wind about 14 miles an hour max. The command and control distance is 5 miles, and that's far beyond visual line of sight, but it just means we have extra communication power. If we have a GoPro mounted below on the aircraft, which we'll see an example of that today. And that's kind of neat because when you stitch it back together, it's like it's sort of flying you around. We've got our standard payload bay and power hookups and a little computer on there so you can talk to it. But the most important thing, especially for the agricultural applications, is that the scientific imager payloads that we've made, they all fit in here. So this means we have multispectral cameras, we have a thermal imager, we have a LiDAR payload we've been working on. They all fit in the same bay. And with that payload installed, a single flight, let's say that we are flying at 2,600 feet above the ground. That means the max battery, max range, all that stuff, 16,000 acres or about 25 square miles we can cover. Or if you launched it and just let it go, that's 120 miles plus of like pipeline or some other thing we can expect. Again, these are numbers based on the hypothetical granting of beyond visual line of sight, but it's still, it's physically real. We could do this today. Also, we have two of these aircraft, one of which is here. Okay, I am going to shift this presentation into neutral. Ian, do you have an update on what's going on out there? Let's check it. We just did a test flight because we thought you might actually want to see it fly. So our crew is readying the aircraft, and basically as soon as they give us the thumbs up, we'll go out and watch a launch. This is the first slide of the next presentation, which Dr. Torres will take over after we launch. So in the meantime, does anybody have any questions for us? We can just pass the mic around and you'll be broadcast worldwide. So the question was, can I talk about the payload? Yeah, I can definitely do that. The payload is something that we've been developing around these requirements, given the limitations of available imagers for a really long time. And where it's at right now is red, green, and blue camera and an near-infrared camera or a selectable filter. So this is something that's a monochrome camera, but we could put various different spectra on. And those are synchronized in time, and they're machine vision cameras. So we get raw images from them, basically as raw as you can get. And we do our own processing of those pixels to allow us to get the best scientific clarity. We've coupled those with thermal infrared imager, which is high resolution, both in space, so it's 640 by 480, but it's also high resolution in the resolution of the spectral data. So basically we're within 1 degree C of the estimate of what the actual temperature is, what we see. And that calibration includes the air column and other environmental effects. So those cameras are all linked together in the payload, along with other environmental sensors that allow us to understand, the air pressure or temperature, those kind of things while we fly. And that's when we say we have the payload, that's those collection of imagers. We've been working on adding shortwave infrared, so a SWIR camera, synchronizing with that. And there's other options for those imagers. The main reason we have those kind of cameras is because when we fly at 4,000 feet above the ground, we need to be able to focus them, so we have really good lenses, and basically we've done the work to pick out an optimal optical path and deliver the finest quality data we can. Okay, so I've been given the thumbs up. Why don't we all get up and stretch our legs?
Row by row.
Yep.
And then move out to the launch area, follow B-Dub out there, and we'll put you right as close to launch as we feel safe and have a chance.
Great.
Take pictures, use your cameras.
Yep.
We'll be live streaming it.
Yep, we will be live streaming. This is recorded. Just stay on the gravel and you'll be safe. So yeah, make your way outside. And for those of you on the internet, I think Brittany is going to log in and give you a view of the launch. Yep, there we go. Might be a little choppy at first, but we'll stabilize that.
seconds of flying forward, if you had good eyesight, you saw those propellers stop to save battery power and aerodynamics. Now the only propeller is the back one flying, and the other ones are stationary, kind of aerodynamically into the wind as it flies around. If you notice, we put the pad on the ground. That's kind of multi-purpose. It protects the ground from blowing dust and dirt and rocks up. It also provides a level landing pad that they can see when they come back in. So it's a safety as well as a visual marker for the ground. And you can see as it flies around now, the pilot can either be manually flying it or they can program it. So once it takes off, they can actually have it follow the autopilot program. And now it flies the pattern back and forth over the field. And then once it gets to the end, it'll reverse direction, have overlapping fields. And when you have an overlapping field, you can gain a three-dimensional picture of what's on the ground. And so that's part of the planning that Cal talks about, is you want to gain the right height, the right sensors, the right angles, the right time of day. All these different types of planning considerations go in. You may spend weeks and weeks planning before you ever launch that mission to make sure that you get the proper payload at the right time, and make sure you have extra batteries, good weather, FAA permissions. All that has to go into that pre-mission planning before you even collect the data. And then you have the fun job, which is to analyze the data afterwards.
That's a perfect transition. Why don't we move over to the trailer and we can all see how the scientific calibration works while the aircraft flies?
Hey, let's go inside and you actually get to see the real data.
So we could go past the trailer.
On the left of the trailer, you can see what where is Alfonso Torres.
Right there, the straw hat.
Alfonso is Aggie's chief research scientist. He is the guy that tells us which requirements we need, and
It's his show now, so we'll let him guide you through the calibration process and then take you back and show you some slides.
all right.
Thank you for joining us today. It's a beautiful day to fly. No clouds, at least no massive clouds. What you see here, there are different settings to calibrate the camera. This is the one that we use, but all of them requires to have what we have an object of reference or a surface of reference, and that's what is called this white panel. This white panel comes from a laboratory that is calibrated, and if you have worked with commercial drone cameras, they also provide a surface reference or a calibration panel to compare. I mean, sunlight is always changing. In the morning, we have less sunlight. At solar noon, we have the maximum, and then in the afternoon. So how do we know when, if we fly early in the morning or solar noon or the afternoon, the data is comparable? So before flying, what any UAV team does is they point their cameras towards this surface of reference. They capture a picture, they capture an additional coefficients or values that then goes, that then is used to calibrate the pictures collected at that time. So because every time, early morning, solar noon or afternoon, you are comparing against the same surface, you can compare the data. So you can, let's say you fly early in May, but you flew at solar noon, and in June you flew at 10 in the morning, you still can compare both data sets, both products, because you refer it against a baseline, a reference panel. So that's what we do here for the cameras, for the, let's say the RGB camera, the infrared camera. Actually, these are industrial cameras. So what we can do with these cameras is not only put an infrared filter on it, we can switch to a filter that is more, let's say, is different. For example, have you ever heard of a filter called yellow or coastal blue? So these are not your red filter, your blue filter. These are intermediate filters that allow you to capture something about the light being reflected by the surface. So the advantage of using industrial cameras, especially in research or scientific setting, is that we can tune up the sensors to what we need. So, for example, I'll show some slides on where the use of these not too common filters help us to solve a problem that otherwise will be extremely difficult to do. And that's that knowledge come from the remote sensing science. Another thing, we have on board a thermal camera, and there are so many cameras available in the market. There is FLIR, there is the MicaSense, there are other vendors. So every vendor will tailor their thermal cameras to a specific market. Some of them will use it for medical purposes that you can adapt it to your drone or you can attach it to the drone. Others are more for drone applications. Nevertheless, the accuracy on the thermal cameras is different from vendor to vendor. There are no standards, and let's say the technology and the products in thermal sensors is still evolving. So how do we know, similar to the example that of when we fly early morning, solar noon, and afternoon, how can we compare? We need a ground control measurement of temperature. Is this little device. This is called a black button. So when I turn it on, the sensor will be telling me the temperature, the absolute temperature of this black ring in here. If I point my thermal camera, I can know how different, what are the difference in temperature between the camera and the sensor. Given that this is an absolute measurement of temperature, I can always correct temperature from the FLIR camera, from the MicaSense, from the one that we use against a reference again. So those are some of the activities that we do to ensure that the data that we collect is scientific, has been adequately calibrated, and it's comparable. Because as we will see, we are not alone in the universe. Drones have bigger brothers, and they're called satellites. So do drone data compare to the quality of scientific satellites data? We will see that on some of the slides we prepared. Okay. Any questions about this process?
How long does it usually take to calibrate all of this?
It depends on the automation. For example, there are commercial cameras like MicaSense or Sequoia Parrot that for them, given that the filters are always constant, you just put the camera on top of the white panel, you hear a beep from the camera, and it's done. It will take 5 minutes. In our case, we have to pay more attention to see what filter is being put on the camera, do we have the right settings on the computer, and then we store that information. So for us, it takes more time, but it's because how we have set up the technology for these sensors. But also the process here is like 10 minutes. So it's quite straightforward. And these reflectant materials are also commercially available. It's just the knowledge of when to take the picture, avoid shadows on the surface, maintain it clean enough. So those things that are important for calibration. Yeah.
So we'll go inside for the next part of the presentation. Just when you walk by the trailer, this is self-contained. They've got a generator, they've got their air conditioning, but all the equipment in the drones can fit here. So when they go on site, They just take this trailer with them, and all the equipment that you see here, they take with them, so they can be able to do the full analysis wherever they go. And they've got the radio tower here, so they can talk to airplanes. So again, they can coordinate and they can even broadcast it with a good internet. So this is what they're designed to do: is to be very mobile and agile in their support of where they go.
Okay. One more thing. The GPS on your phones, on your internet devices, has an error of 10 feet, any direction, and the error is random. So today is 10 meters to your left, tomorrow could be to your right. The same happens with GPS on board on drones, any drones. How do we know that if we flew in May and then we flew again in June, how we make sure that the pixels from these two different dates fall in the same spot on Earth? We use ground control setups or ground control targets like this one. So you toss these guys, you toss them around, and typically you have a total station or a GPS station, and you capture the coordinates of where these ground controls are located. And when the data is processed, we refer or we force the image produced by the drone to match the coordinates of these locations. Now, the one that I'm holding here is the next generation of ground control devices. This one has already its own GPS, and we have a full bag of them. So instead of taking additional GPS equipment, we just toss them away and we turn them on. So if we left them out there for 45 minutes and they have captured enough information from the GPS satellites that their accuracy is ±1 inch. So when we come back in June and fly the same spot, this guy doesn't have to be in the same spot, but my data from May, from June and July will align perfectly. So I can compare plant against the changes in the plant from any time the data was captured. We can compare other features and we can integrate it into GIS systems. So this is the radiometric control, the camera, the white panel, the black body, and this is the geometrical or the spatial control. So these two elements have to happen when you use drone technology.
I have a question on the airplane. On the airplane.
Yes.
So as your square footage scales out,
Yes.
do you have incrementally? Do you know how many airplanes you add to the?
So 10 of these are supposed to cover 180 acres. So proportionally, as you increase, then you buy obviously more. 10 comes in a set.
Yes. Hey, Dr. Torres, want to get these folks out of the sun and show
Yes.
us?
Let's head back inside here.
So hello again, everyone. If you have been watching our demo, we've been kind of moving between the in-person interviews, and I think Ricky Loveland here is sharing the actual ground control station screen, so you can see what that's like. We basically have the actual ground control station, Q ground control here, and we're just orbiting the aircraft around the farm here. And then off on the left, we have the Focus Support airspace awareness tool, so we can see everybody's locations. While everyone's filtering back in, I am going to switch us over to me again, and I should be able to bring our slides back up. Let's see about questions. How many other people are watching on the Zoom? Good question. I think we are at 16 attendees. So with 4 panelists, there's 20 people on the Zoom. Good question. Let me try to switch back to share my screen. Okay. So now I've got video of me in the corner. We should be able to convert to Dr. Torres' slideshow. Okay. Alfonso, why don't you go give them one last warning and then start? Okay, they're coming. Let me turn up the microphone just so everyone can hear us through the masks. All right, Alfonso, take us away.
Well, hello everybody. My name is Alfonso Torres, and I'm originally from Peru, and somehow I ended up here in Logan, and it has been fun. Uh, I'm going to cover the rest of the slides on this presentation, and these slides are about applications. So early in the morning, we saw about the aircraft and the necessities for planning a mission and making sure that we have the right sensor, the right technology, the right uh, and the right capabilities to collect the data. So then we go into the collection data mode, which is the calibration of the cameras, making sure that the thermal camera is adequately calibrated, the ground control. So now, what happened after that? What can we get, or what are some of the products that we can get from using UAV technology? So continuing what Cal was saying in the presentation, we have and we have different type of UAVs nowadays. We have the multi-rotors, we have the fixed wings, we have the, let's call it the experimental fixed wings, the larger fixed wings, and then we have satellites. So we, as as we use this type of information, we cannot forget that there are different type of platforms in terms of UAV, but also we have additional information that comes from satellites that NASA private organization have launched into space and provides similar data, although on a more larger scale. So nevertheless, in agriculture, which is the area that I focus more my research, and you see a nice picture here, we all work together to provide the information. Satellites and drones can work together to inform the farm manager, the irrigator, or the, uh, the agricultural company about different questions they have about their crop. And the same statement can be applied to natural environments, can be applied to urban areas too. If we want to do a comparison between satellite and, let me see if I can move this guy. The best satellite that we have in space in terms of pixel size and UAVs still provides the finest level of detail uh, uh, for a given feature. While satellite can provide us the landscape understanding of conditions, the UAV provides us the finer details that we might need to address certain questions. So to give you an example, and this is to tie what we talk about the cameras, what we talk about calibration, what we talk about planning the mission. Do you recognize this place in the picture? All right, our beloved Utah State University quad area, where uh, uh, where we can apply, or we can see some of the effects, or we can see what the sensors see that we as humans cannot see. So a year ago, we did a flight over the quad to see what these different sensors can detect, just to experiment how turf grass is seen through the lens of a UAV camera. So here you have 4 screenshots of 4 different cameras on board of a UAV. The, in this case, your top right is your RGB. No, your top left, in this case, is your RGB camera. In your top right, you see the reddish, the one that is showing the vegetation as red is the infrared camera. And there is a reason why it looks red. It's because plants reflect a lot of infrared light. If we were able to see it with our eyes, it will be like looking at red snow in a sunny day. That bright, that level of brightness is expected from plants. It's very, very intense. So that's why this image looks very reddish. The bottom left, the yellow, the one that shows the vegetation in yellow, is what we call it a red edge camera. Is it as you can compare it with the RGB and with the near infrared pictures, what do you see on the turf grass in the quad? There are some features. It's showing some kind of circles, right? On the reddish. What is that? Those are the sprinklers that the irrigation system in the quad uses, but we can see that the irrigation is not homogeneous. Despite what we might see, and actually we can see it if we walk around the quad, we need to slightly improve the irrigation system, but the red edge camera allow us to see where we have issues on the irrigation system, uh, that the RGB camera and the near infrared can tell us, but the red edge tell us more. The last one on your bottom right is a thermal picture. And the thermal camera is telling us, well, the sidewalks are hot, plant is cold, some part of the sunroofs on the buildings are colder, and this is because they are probably mostly metal type sunroof. But is the temperature of the plants homogeneous in the quad? There is this area which is colder, and that uh, and the and that means either that location has more water in the soil, so that area needs to be irrigated less. The hotter areas in the quad might require slightly more water. And that's how we use, I mean, that's a very a simplification of how we use thermal cameras. When a plant has water in the leaves, it's colder. A dry plant is hotter. So a healthy plant have water in the leaf requires less irrigation than a plant that has less water in the leaves and is hotter. So that's an application of thermal cameras. Just to give you an idea, so the RGB show us the world as we see it with our eyes. Green is green, red is red. But when we move to other type of sensors, we start seeing issues that our eyes and RGB cameras cannot. And that's the science of remote sensing, or understanding uh, what each camera can provide. So this is, let's say, the first level of understanding of sensors on drones. This is an RGB image of Fish Lake here what do you see? Well, you see this, you see the lake, you see the shore, you see the trees at the bottom of the image are already provided yellow leaves, right? But can you see inside the water? Something, right? But can you see how much vegetation is inside the water, inside the lake? This is an RGB camera. What if we switch not to near infrared, not to red edge sensors, but we switch to those called coastal blue and yellow? You see through water. So certain type of light can penetrate the water column and bounce back to the sensor of to the camera. So that is another application of drones. When well used and the characteristics of the location understood, you can get meaningful information that allows you to see and detect properties or conditions that otherwise are not visible. And for example, when we're using this camera that has coastal blue filters, yellow filters, the vegetation and the soil that around the lake doesn't resemble their traditional colors. It's more whitish, grayish. Vegetation has this purplish color. So, but that's what is the initial level of manipulation of data. Using these spectral filters and displaying them so we can infer what's happening with our eyes, we can infer what's happening in the image. There is a next level of image processing or analysis of the data. The next level is on the top left, you have the UAV image, the RGB, and we are not showing here, but we also have thermal data, we have infrared data. We start processing that data at pixel level. We're not, so what we're doing is, okay, we can detect these conditions in the ground by doing ground measurements. And we say this vegetation is phragmitis, this vegetation is field moil, this location is bare soil, and we can do what we call it a classification analysis. And we can generate a land use, land cover map. If I want to detect the health or how healthy is the vegetation, I calculate what is called a vegetation index, which is an algebraic equation that I apply to every pixel. And that index, one of those index is called the NDVI, the Normalized Difference Vegetation Index. That tells me how healthy is a plant, but from a rank from 0 to 1, 1 being the healthiest and 0 being water, and use above 0, bare soil. So I can detect or I can do a quick quantification of how healthy is the vegetation in that area that I'm interested. But I can keep pushing that. So on the bottom, on the image that says LAI, LAI is a measurement of biomass, or how much leaves that pixel has. So I might have trees, I might have turf grass, I might have wild grass, I might have corn, I might have alfalfa. I can quantify the volume of leaves at pixel scale. So that is another level of processing, an algebraic processing of the pixels. Now, the last one that we have here is the FC, or fractional cover, which is telling me for every pixel that I have in the image, how much, what percentage is soil, what percentage is vegetation. And that is important to see if that area is fully covered by vegetation, or you have dry spots in your image, and what is the amount of that dry spot. So this is the next level of image processing in drones. The generation of vegetation indexes, classification maps, and some basic biomass quantification. So there is one more level of analysis, and this level is the same type of analysis that is done to satellite data. And this is the integration of sensors on the ground, UAVs, and information from satellites. What you're looking here, it's a project that we have been working in collaboration with multiple institutions, as you see the logos on the bottom of the slide, that with experts in different fields, from uh, plant physiologists, uh, farm managers, scientists on satellite information, scientists on water use. The idea is that we can transform that pixel information into estimation of plant water use. So per pixel, we can know how much water the vegetation present in that location is using it. And the same analysis that is done to satellite data at planetary scale, that is done at continental scale, that is done at a state scale, at farm scale, and with UAVs at plant scale. All of them giving the same information to farm managers, canal companies, uh, water agencies, federal agencies. So this is the third level of what we call it analytics. The first level is to visualize the image. The second level is the algebraic manipulation of the pixels to derive some information. This is the third level. This is the application of mathematical models with local information to produce this type of information. So AggieAir and USU has invested for more than a decade in the AggieAir program. And you can see some of the advances and, and results that have happened due to that investment. We have a unique set of tools, aircraft, sensors that allow us to target difficult, different questions that might occur or are present. Uh, for example, you are seeing a multicopter there flying over vineyards. On the other picture, you see something red on one of the aircraft legs. That is an air sensor. So it's not only collecting images, but also air quality sensors and other type of miniaturized sensors could be flown. For example, now that fire or wildfires are happening in California, air quality is going bad. Can we collect air quality information with drones? Yeah, we we can mount those sensors, and has been done several times for the state of Utah and in different applications. Sensors, miniaturized sensors can be mounted on these drones and information can be collected. And as well, always having the or taking care of the radiometric and the positioning accuracy of the data is important. So what we were able to do, all right, sure, all right, fine. So the Aggier team went to California this summer, and we took this new aircraft, we call it Dark Horse, to collect data in two different sites. along with uh, air information. So this is not your typical UAV application that you go, fly, collect data, and land. In this case, the aircraft has to fly these two blue polygons. Then it has to do the orange line. Why? In the small polygon, there is a very is there is an advanced irrigation system that can control the water apply every 100 feet. On the large blue polygon, we're collecting as much data as possible from vineyards and almonds. And the orange line is to collect air information about that location. So how much data the UAV produces in one single flight? Well, with per flight, it can collect over a quarter of a terabyte, which is massive. And those are some of the challenges we have to think how to improve data download from the aircraft because it's massive. It's massive just to collect it. Is even more massive when process it. So uh, with this new type of aircraft, we are removing the restriction of area, but we're adding another problem, which is storage, processing of this data. And that's a good challenge for us. That's a good challenge because for UAVs to respond to the dimensions of American agriculture, it cannot fly small. It has to be able to respond to those dimensions. And we think this type of platforms can be the answer for that. All right. All right. All right. So this is air temperature, but vertically with that orange sensor. I'm not an expert on this. I'm more a pixel analysis guy. But what you are seeing here is this air turbulence happening over agricultural farms that is telling us something about the interaction of the atmosphere with the surface. So in other terms, if we have a fire and this hot air is blowing over agricultural land, how that affect the water use of the plant? So the team that we're working on is looking at that air information we collected from them so they can see what's the impact of fires over agriculture and over water use. And we have instrumentation all over the place. And one of the beauty of these, of the data coming from UAVs is that we can see the instrumentation. We can see the sensors itself. So if the sensor is measuring a particular plant, we can relay the pixel information to that plant. So we can do a very precise comparison between pixel data and sensor data. And that is good because then when we develop this relationship between the sensor and the pixel, we apply it to the entire UAV image, and then we compare the entire image of the UAV against the satellite pixels over that location. So we integrate ground sensors with satellite sensors by using UAV technology. So, and that's it for this presentation. What we want to be in AggieAir? Well, we want to demonstrate and we want to push the technology, the capabilities of UAVs in the, let's say, in the research and development area with new aircraft, new sensors. We want to address those questions that cannot be addressed by satellites, but also we want to develop to to develop methodologies and technology that can integrate more those ground sensors and those ground measurements with satellite information. So we get a uniform answer from sensor all the way to landscapes. Any questions?
Thank you, Alfonso. You are perfectly able to ask questions, but let's save them until after the landing, which is the next thing on the agenda. So if we could all file back outside to the viewing area, we'll be landing shortly and you guys can get to see that. And then we'll come back in here for some Q&A and cool off. So see you soon. And those of you on Zoom, I will convert to a reporter in the field.
Altitude there. Just read that off. Like once I open it, line it back down. A lot of these means your eyes aren't in the goblet. Yeah. I'm watching it. You're good, Kevin. All right. Yeah, when I don't worry about it now, but just know where it is. Just read that off.
When it's about that position on the next loop, that's when I'll take control of it.
Okay. You'll still probably need to control to the map. So
how much battery do you have?
Most of it.
When it gets to like that position, I would just plug it in and have it chilling on the ground for now.
I just don't want to like BTX gets real hot. Way too long.
You'll be fine.
So
I leave my quad chilling in the sun at the strip events for like 10 minutes.
Ooh.
Yeah.
You need to treat it nicer.
Works fine.
Also probably trying them.
Yeah, you're probably right. Austin. Thanks for that demo. That was great. What's our battery like? That's like a third what we could do, basically.
Yeah, we only use like half of our fixed batteries.
Okay. Yeah. So this thing basically will fly until you get bored. So, but before that happens, let's head back inside for some Q&A and wrap it up.
Yeah. For those who have to go, I just want to say a huge thanks to AggieAir. If you can't join us for Q&A, please, look online. They have a great website with lots of information that we didn't cover today about their history, their projects, past stories that they've done. But if you've got a couple of minutes, just come join us in there and we'll have a chance to do some Q&A with any of the AggieAir staff or education or Dr. Miller. We'll have a chance to do that for a few minutes. So if you can make it inside, let's go in and do a wrap up. But if you have to leave, I know it's about 3 o'clock, so that was the time commitment. Thanks again for your participation here today, and for all those who are here, look up Aviation Utah State and see where we're going to go. We hope to be bigger and better every year, and this is what we're all about: is to bring education, research to the community and to the nation and the region for agriculture. So thank you again. But let's head back inside for some Q&A.
Oh, cool. I remember that. Yeah. So, you guys.
You have to swallow your breath. Yeah, if it's too close to the ground for too long, then you just.
Okay, well, thank you guys for coming back inside and cooling off. It's surprisingly warm for being winter. Before we wrap up, no questions from the Zoom attendees. Now's your time to get those in if you guys want to ask something. Do you guys in the audience have any questions? And if so, take the mic and speak.
So transitioning from an automated flight to a manual piloted flight, what kind of complications or what kind of intricacies do you have with what we just saw?
Okay, good question. Thank you for asking that. With the autonomous flight, there's a couple of different modes the aircraft operates in. And one of them is fully autonomous, which means it's on the ground and it's hot and you hit a button and it literally takes off by itself and another button will land it. And those procedures happen in concert with the forward flight, the transition mode. Basically, when it gets off the ground, we have to turn on the big prop as you saw, and then the quad rotor system needs to shut off. And so there's different parts of the state machine, basically the mission that it flows through. And the pilot, which we saw, the takeoff and landing is basically manual. So that's a different mode of the aircraft where the pilot's in control of those modes, whether it's taking off, landing, whatnot. And actually in the direct manual, the pilot has his thumb on the throttle and can control the energy that's going through the aircraft. So there's a wide array of various autonomy levels. The pilot's in control of that. And the reason is we don't want to do fully autonomous flights if we have other aircraft around, that kind of thing. We have to talk to the airspace. Or if the weather's good when we launch and 2 hours later it's bad, the pilot's going to want to put it into a manual mode, which is just a switch on the controller. And then they're in control and the autopilot's just basically telling them facts like speed and battery. And it's not actually in control. So when it comes down to it, it's a software platform that allows you to interface with the aircraft. And then it's the pilot's training. So it's up to experience and basically what's legal, and the pilot's in charge of that. And as the Baron was saying at the start, we have licensed pilots who are registered with the FAA, And if they have a safety incident, they need to talk to the FAA and they need to go through all that and everything. So this is a tool. The autonomy and the manual is a tool to allow the pilot to safely operate the mission. Great question. Great question. Any other questions? Wow, stunned silence. That's the best I could hope for. Oh, there is a question online. Sharp eyes. Are you working on an abort flight function for the auto flight? If bad weather came up, you could just hit the abort button and it could take itself back to the landing zone and land itself without manual flight. That's related to the earlier question. When we take off, the autopilot saves the GPS location of the takeoff point. And so we have that waypoint to come back to. And if we lose communication, or if there is some other abort condition, for example, like the operators have no other way of talking to the plane except mashing a button, yes, there is a return to home and land part of the mission, but we only execute it if we think we need it. And usually we want the pilot in the loop doing a manual landing because this thing's a little bit delicate, but that's already built in, and it's part of what we would call the failure tree, where the CONOPS, the concept of operations, is if some kind of exigent circumstance happens and there's a safety condition, yeah, we can do a return to home and land, or we can even do an abort in place, which basically turns on the vertical system right there and lands it anyway. And this came up earlier, and maybe the wider eyes didn't hear it. We have two separate power supplies for this aircraft. One's for the vertical lift system and one's for the forward propulsion. And that means if we have a problem in the air, we can always cut the forward propulsion and use that vertical system to glide to the ground, or at the very least take energy out of the aircraft, which is equivalent to a parachute. So it's actually not just a landing system, it's actually a backup safety system, in which case it adds to the failure tree and the options the pilot has for abort or the mission planning in case the pilot can't talk to the aircraft. So wonderful question. Yes, I would say in summary, that kind of stuff is built in. It's all part of the platform. Yes, another question.
Okay, so for your pilots, as they're learning the system, is there a standard amount of flight hours that they have to become quote unquote operational to one of your studies?
So that's a wonderful question. And to answer that question, I'd like to bring the Baron back up here. Before he says anything, I will say it depends on the aircraft. And the GreatBlue aircraft is very heavy and it's quite precious, so it would take more practice to fly it. But there are legal answers to that question.
Actually, that's one of the most important questions right now. So if you go to the FAA, to be a drone remote pilot, there's no flight test and no flight time required currently. They're changing that, and I don't know if it's going to be this year, next year, or 3 years down the road. So for anyone that wants to get their certification, now's the time to do it, because you can just take the test. And Utah State University offers some courses, and we do in-person and evening courses outside of curriculum, which are concurrent enrollment or continuing education courses. But right now, it depends on the type of airplane and who owns it. So right now, the operator, AggieAir, determines who can fly it. We're creating a class this spring with Intermediate Flight Lab and Advanced Flight Lab to train our students to fly more complicated airplanes. And so there's just a select few that are now certified to fly it. How many do you have right now? 2? 1? Because one's in the hospital. 2 are certified, and so it's just by the owner operator. And so that's what you look at. And so you start with some of the basic ones. You can use some that have a lot of automation. There's a lot of the DJI, the Mavic, there's Altel, there's numerous ones that we teach people how to fly, but there's a lot more automation in the quadcopters or multi-rotor. It's the fixed wing experience that we're also trying to teach, and so we emphasize that with the education program. But that's a great question, because right now there is no FAA requirements, and so it just depends on the type of airplane and the risks they're willing to take. You have a $15,000 drone, you're not going to let everybody fly it. You start getting a $100,000 drone, you're going to have your own certification program and determine what type of skills. It's be more skills based than hours based. But some of our drone pilots that are flying with the AggieAir, they've been flying hobby for 10, 15 years. And so they have a great air sense and a great hands with the controllers, which makes it easier to go from one vehicle to another. Just like once you learn how to drive a car, you can probably drive most cars on the road unless it's a stick shift, right? But once you learn stick shift, you can probably drive most stick shifts unless it's a semi truck, you know? So the more complicated you get, the more challenging the certification would be.
Great. Another good question. We have another question online. The question is, does the platform have the capability to switch between flight modes and hover in place in mid-flight to get detailed footage of a specific target? That is an excellent question, because as we noted earlier, the platform that you saw today is a hybrid between a fixed wing and a vertical lift system. And it is heavily biased towards the fixed wing side, meaning all of the power efficiency and basically the flight time is in the forward direction. And that means that the battery packs that take the aircraft up basically out of the ground effect and into a place where it could transition into forward flight and then return it, the entire system on this aircraft can only last about 2 minutes. And so that means our pilot is basically trying to get it into forward flight as soon as possible, and then trying to break it back into the quad rotor mode, the transition and reverse as soon as possible, and land it, and to spend the least amount of time in that quad rotor mode in case we need extra energy. And so the question online is kind of like, could you fly the fixed wing craft out to a specific place and then turn it into quad rotor mode and basically have it station keep over a particular spot? And the answer is technically yes, although we probably wouldn't want to do that with this system because we'd need that power for landing or if there was an emergency. And that's why way at the beginning, if you guys remember, I showed the different kinds of drones. The traditional hexarotor, quad rotor, or whatever lift system, your DJI Matrice, that kind of drone is a lot better at that station keeping because that's all it does. If you wanted to design a system that could fly, let's say 50 miles, 40 miles away, and then station keep for an hour and come back, you need a different kind of power system because batteries just can't do that. So this is a compromise between those different things. And it's the GreatBlue platform is really, really nice because, you know, takeoff and landing is simple compared to the launcher system. Recovery is nice and everything else, but it's not really designed for the hover flight. That's a great question, though. If you have a hydrogen power system that's converting the hydrogen to electric energy, that kind of thing, then you might actually be able to put that much electrical energy into those props and have that. But the traditional upgrade from the system we show you today is instead of the electric forward propulsion, you would have a gas engine. And that would give you like 6 to 8 hours in a similar sized aircraft with a fuel injected micro, you know, aspirated engine. So I know that's not quite the answer to the question you wanted, but yeah, right now technological limits say you just need a regular VTOL for that. Great question though. Great question. Anyone else in the audience? Okay. Well, if there are no other questions, if there are, bang them into your keyboards remotely, or email me or any of the other folks. Our contact info is always out there, Twitter, Facebook, etc. However you found this link, please follow up with us. If that's it, then I would sincerely like to thank everybody who came to see our demo. I would like to thank the College of Ag profusely for the venue, the Baron for arranging all of this stuff, bringing chairs, etc. Thank you to the AggieAir team for putting that demo on. That was amazing. This was really, really great. And again, follow up if you guys want to play along with us. We've got a lot of cool stuff going on. Or if you have questions, we believe in autonomy bettering society, and this is one of the ways we really think we can really help out, save water, etc. So from the bottom of my heart, thank you all again, and we'll catch you at the next demo.
Thanks, Cal. Just one last shout out. If anybody has any questions about the education side, please come to fly.usu.edu, look up aviation and our new drone programs about the research side. But one closing comment is you saw that there was quite a bit of team here. It's not just one individual going out. You can, on a small scale, be sole operator where you're the planner, the operator, the sensor data and collection. It is possible out there. But for some of the technological advances that AggieAir does, it's a team effort. You can see that they can bring out their full team. I think the minimum team that normally about 4 or 5 people to go out because you need to have all those resources. And so if you want to get more experience with that and come and partner with AggieAir, let them know. They're looking for research projects. They're looking for ideas, and not just with Utah State University, but with all partnering with industry. And so that's an opportunity. So again, thanks to everybody for supporting us here today. Please keep in contact with us so that we can continue, and hopefully we'll be able to do this again next year and have bigger and better platforms. Thanks again. Have a good day.